Okay, so you should have been introduced to the ideas of elongation and strain, and then load and stress. And so we're talking about this concept of tensile material testing, having a sample in the shape of like a dog bone and putting it into a machine that can pull on it, put it in tension, and start to track and measure these forces and distances that are happening as the material starts to deform and stretch. And so we had talked about in the previous video that we want to eliminate test results based on the sample size, how big of a dog bone we used. And so in order to do that, we take, we'll just go in the order of the handout, we take force, how much force we applied, divide it by the cross-sectional area, and then that's called stress. Obviously, a bigger, thicker sample is going to be able to handle more force. So by dividing by that cross-sectional area, we're figuring out, how much force per kind of unit area of that cross-sectional area. So, right, one pencil versus maybe putting 4 pencils together. This has, cross-sectional area, say, of 1 pencil, right, 1 unit. But I don't have 4 other pencils sitting right here, but your pens, versus if I had 4 together, this, in theory, might be able to hold 4 times the force. Okay, so anyway, we're dividing by that area to try to help us get down to something that ignores the sample size and gets down to a unit ratio. So per unit of area. All right, so that's called stress. It has to do with the force that's loaded. So how much force, how much stress are we putting under? As the object starts to stretch out, we have what's called elongation. The amount of stretch is called elongation, which is this symbol. And a longer thing is going to stretch more. It's just a lot more material to be able to stretch than if I had a really short sample. So I can't get as much stretch out of a small length as I could out of a long length. And the reality is that's because for each unit of length I add another bit of material that it itself can stretch out. And so again, we're trying to remove the variable of how long my sample was and just understand the material that per unit of length, how much stretch might I get? So that's called strain. So the amount of stretch divided by the original length. And here's the elongation symbol. Okay, this is the symbol for strain. This represents the original length. Okay, so we can graph and plot stress and strain. Okay, and so as we add stress on the y-axis, okay, if we start plotting, what we expect is that the material is going to represent, it's going to experience strain. That it's going to start stretching out. So we're going to get some elongation, some measurable distance. So, right, that's what these core principles, that we're loading force and we're getting stretch, but we've normalized it down to unit rates. So as we load it and we put it under stress, it experiences that stretch in the version of strain, starts stretching out. Okay, so here's the general shape of the graph. You've got this linear part of the graph. Okay, for a while this is a straight line. The slope of this line actually has significance, is on the next thing, and then it goes into an arc. So let's really look and understand these key points of the graph, okay? But this is a graph of stress over strain, but we'll see where we're at. So this blue region here is called the elastic range on our stress strain graph, and what's special about it is mostly it's linear. There's no curve to it. Physically, the property is that the material, you loaded it, you applied some load. Yes, you did get some amount of stretch, so the material moved. Okay, it had to, because we've got ordered pairs that are to the right. So we've got some amount of stretching happening per unit of length. However, if we take the load off and we're still inside this region, the material has not been damaged. It'll go back to its original length, its original size. Okay, there is a region in which we can operate where we can load a material and release that load, and the material has not been damaged. It'll go back to its same. Okay, so key things, right? Load removed, you're going to get a copy of this handout. Sample returns to the original length. Stress and strain are proportional. They are linear, proportional. It's like a ratio. as you keep taking the same size stair step. So if you think of slope, it's constant. So equal ratios is proportional. Okay. Eventually we hit a proportional limit. Okay, there are some key points here. A proportional limit is the point in which it stops being linear and it starts to curve. All right. That is not the end of the elastic limit. The elastic limit would be slightly past it. It'd be yet a different point, but they're very close to each other. So the elastic limit is the end of that elastic range. It's the end of the range where the material has not been damaged and it will return to its original length. Okay, so that's the key of the elastic range, is that we're still within the limits of operating so that our material has not been damaged, that it goes back to the original length. Okay. In regards to the elastic region, okay, if you were to drop a vertical line, so like an altitude straight down to the x-axis, okay, the area under the curve can be calculated. It's just a triangle right here, and that is a value. The area of that is what is known as resilience. So that would be a numerical way to compare materials as to, you know, how much energy can that material absorb and handle. So something that's very stretchy, like a rubber, is going to have a lot more resilience. It's going to have the ability to handle a lot bigger impact, more energy per volume than you know, something else. So that is kind of a cool little thing, is the area under the curve. You have to go straight down from the end of that elastic region. That represents resilience. So the greater area we have, the more resilient the material we have. Okay. All right, so moving on to the next range. So moving past this elastic region, and we're getting into this region, and we find ourselves with what's called the plastic deformation region. And this region represents failure. The material has been deformed to the point that it's never going to go back to its original size and shape. So we've actually damaged it. It hasn't broken and separated yet, but if you take the load off, it's going to look different than it did before we loaded it. So this little graphic here with the necking happening, you take the load off, and this is not going to go back to a nice smooth cylinder anymore. That's permanent damage. Okay, so within this region, we want to have a couple things to point out. As we're kind of loading it and experiencing more and more stress, let's talk about this one first. It's the yield point. Okay. The elastic limit has been exceeded, so we're definitely past it. Okay, at this point, we'd say a small increase in force. Okay, so increase in force would be this way, vertical, right? More stress results in more strain, right? But the ratio at this point is different. A little bit of increase in stress to get to that next order pair creates quite a bit more strain. So you can see how the stair step is not as steep anymore. So a little bit increase in stress creates a lot more strain. Okay, so we are definitely into, at that point, the kind of the failure mode. But even though a little bit of stress creates more strain, we can continue to load it more. Eventually, we'll hit our peak, and this is the ultimate strength point. The graph never goes above this point. That's the highest. Okay, if you track over to the y-axis, what's the highest we ever get to, and that's it. That represents the ultimate strength. Okay, at that point, the material actually begins to, even with less force, experience more and more strain. It is failing, and it's eventually going to break. Okay, at that point, that is when this happened, and it is broken. Okay, right here. So, we have a couple graphs here for you to compare and contrast the difference in material that would be ductile, that would be more stretchy, versus something that's brittle. So something that's brittle, if you try to bend it, it's not going to bend at all. It's just going to snap and break. So the measure of ductility, okay, less ductile is brittle. More ductile would be more kind of more resilient, more stretchy. If you look at these pictures here, the last picture is one that is very brittle. It's very flat where it broke, and so that is just what occurs when something that's really brittle finally hits its breaking point, as opposed to something that was ductile. You're going to get this concave kind of cone-shaped recess. The opposite end will be concave, one will be convex. All right, and then underneath the whole graph, we could find the area of this whole curve, okay, under the curve, just like we talked about with the area under the elastic region representing resilience. The area under this whole thing can be measured and calculated, and that's a representation of how tough the material is. So hopefully that gives you an idea. And the next phase will be looking at some formulas and understanding some of the calculations we're going to perform.